Boom! Alright. This is where the thing getting real exciting now. So in the video before this one, we did a brief, well, it wasn't so brief, right? But I'll get the point. We did a little discussion on the general idea, the general concept of gradient. Right? We talk about gradients of whole numbers, whole number gradients, sorry. And we talk about fractional gradients, we talk about positive gradients, and we talk about negative gradients. So we're going to do some examples here now. So we have two line segments. Be very specific with the language now. Line segments meaning that this is just the segment of a line, which you could get by extending the segment in both directions as far as you care to do. Right? Same story here. This is a line segment. Remember that any 2 points define a line segment. So you have this point A21 and this point B45 defining this particular line segment. And then you have this point C minus 21 and D minus 45 defining this particular line segment. Good. So we're going to now find the gradient of both of these two lines and demonstrate the concept even further. Now remember that for any line segment, provided of course that it is not horizontal or vertical, we could extend outwards and get a right angle triangle. Right? Remember that is how we found the distance between the 2 points, or the length of the line segment. Right? So we have the liberty of doing a quick recap of that. So in this case we came across like this, and then we came down like this. Right? So that there is a right angle. So to find, let me just draw the whole line under. Right? So that's the right angle there, which we got by extending outwards. So in other words, we were able to find the length of this line segment using Pythagoras theorem if we found the length of this line and the length of this line, which we could very easily do by a quick visual inspection on your coordinate geometry system or on your graph paper. Now we're going to use the same right angle triangle to define the concept of the gradient, because remember that the gradient is defined as the ratio of the vertical distance to the horizontal distance. So in other words, for each unit of vertical movement, you have a certain amount of units of, for each unit of horizontal movement, you have a particular amount of vertical movement. Right? And to do that, all we do is divide for any 2 points, we have the line segment, we divide the vertical distance by the horizontal distance. Good? So in this case, we have the vertical distance as what? 1, 2, 3, 4, 5. Well, we're starting from here to here is 1, and then from here to here is 2, from here to here is 3, and from here to here is 4. So this vertical distance is 4, and we can see that this horizontal distance is 1, here to here is 1, and here to here is 2. So this horizontal distance is 2. So that the gradient m would simply be, I'm writing it up here in red, m would simply be 4 over 2, which is equal to 2. So your gradient here is equal to 2. Now we come across here and we do the same thing. So we extend to get the right angle triangle. You come across like this, and then you go up like this. Right? That there is your right angle triangle. So again, vertical distance from here to here is 1, from here to here is 2, from here to here is 3, and from here to here is 4. Your vertical distance is 4, horizontal distance here to here is 1, here to here is 2. However, remembering that in this case your vertical distance is going to the left, what we could do is actually express this as minus 2. We could do that, right? But I wouldn't do that for now, right? But that is essentially what it is. In fact, I'll leave it as minus 2. Good? So that while the ratio is the same, in other words, the magnitude of the vertical movement is the same in both lines, and the magnitude of the horizontal movement is the same in both lines. So the ratio will just simply be 4/2, which will give you the angle here. But we'll come back to that in a little bit, right? We call that alpha. Because this line is not the same as this line, then there is no way that we could reasonably say that the gradient of this line is the same as the gradient of this line. What we could say, however, is that the magnitudes of the respective gradients are the same, right? So the magnitude of the gradient is the same, but because the lines pointed in opposite directions, we will ascribe a positive sign to one and we will ascribe a negative sign to the other. So again, because the right side has been the convention for positive since whenever, right? There is no genuine mathematical reason why right is positive and left is negative, right? That's just a convention. Somebody somewhere at some point decided to do that, and we have been doing that ever since. So this gradient will be positive and this gradient will obviously be negative. Okay? So in this case, your m would be, we can say 4/-2, which will give you -2 as the gradient. Good. So we have the idea from an intuitive point of view. We were able to put two lines on the board and derive the gradient by simply looking at the counting the actual distance manually, right? Again, before I continue with that point, let me just talk about the alpha here. The tan of this alpha will obviously be 4/2. So this alpha will be tan inverse of 4/2, which is 2. Tan inverse of 2. Similarly here, the angle itself will still be 2. Excuse. The tan of the angle will be 4/2. So anytime we're talking about the trigonometric ratio, we're no longer dealing with the direction. Right? Let me get that clear. The direction only comes into play when we're talking about the gradient, not the ratio. Right? So we could describe gradient then as a vector quantity. You see, I throw in some high language, that's all I know, right? Which you will have to deal with in section 2 when we come to vectors. And for those of you who don't add maths and physics, you know what I'm talking about. So your gradient is a vector quantity and your trigonometric ratio is a scalar quantity. Good? So your scalar quantity will always just be positive, right? Your ratio will just be +2, right? 4/2, that's your tan is 4/2, right? Of course, that would work when the angle is acute. We know that the angle is, we have a slightly different situation once we cross 90 degrees. Again, that is advanced people. So back to where we were going with this thing now, right? So we have put the two lines on the board and we have been able to demonstrate the concept of the gradient. Now what we're going to do is start putting a formula together so that we could then just find the gradient by simply substituting the coordinates into the formula without the need for this, right? So we're now putting ourselves in a position where once we get the coordinates of any 2 points on the line, we could find the gradient of the line without necessarily having to see the line on a sheet of graph paper. So notice that just as we did in the situation where we were finding the length of the line, we know that this distance here is the same as the difference in the y coordinates, right? So your 5 minus this 5 minus this one will give you this 4 here. And similarly, this distance here is the difference in the x coordinates. This 4 minus this 2 will give you this 2 across here. Right? So what we could say then is that we can start saying that the gradient m will actually be 5 minus 1 over 4 minus 2. So those of you who already familiar with the formula, if you would have taken the time to get to this point in the video, you know where I'm going with this. And for those of you who this topic is a kind of new thing or you didn't really understand before, you're getting a sense that we're going somewhere. Alright? Which is equal to the same 4 over the same 2, which is equal to the same 2. Similarly, on the other side here, the difference between, well, this length here would be this 5 minus this one, right? The difference here, while the actual magnitude is 2, we must start taking the direction into account, because going from here to here is not the same as going from here to here. Alright, so the difference here, just as we did over here where the coordinates were all positive, we're doing the same thing here. Of course, you just have to be mindful of your signs. So in the same way that over here, this distance was given by this 4 minus this 2. Over here, this distance will also be given by this 4 here minus this 2 here. Right? So, or can we say minus 2? Yeah, we had to keep the coordinates consistent. So if we take this coordinate from this one and we minus this one, then we had to take this one and minus this one, so that we could then say that the m in this case would be the same 5 minus 1 here, because in both cases we're going up, but in this case, because we're going to the left, will be this minus 4 here. We had to keep the points consistent now. Minus 4 minus, watch it now, minus 2, which would be 5 minus 1 over minus 4 plus 2, which would be 4 over minus 2, which would be, guess what, minus 2. Good? So that's basically it. So after this now, the next thing I'm going to do is do a couple more line segments where you have a positive and a negative gradient, where the gradient is a fraction. And after that, we will get into the general formula for a gradient, and then we will do some examples to drive the point home.